5, 12, 13. These numbers look familiar. They form one of the most well-known Pythagorean triples. Surprisingly, there's a fascinating hidden pattern in these triples. I'm sure you've never heard of it. Take the two odd numbers, 5 and 13. Their average is 9, 3 squared. The difference between the average and either number is 4, 2 squared. Now look again. 5 is 9 minus 4, 3 squared minus 2 squared. 13 is 9 plus 4, 3 squared plus 2 squared. Now multiply 9 by 4, and then by 4 again. That's 12 squared, the even number in the triple. Coincidence? Let's test some more. In each case, if you take the average of two odd numbers and multiply it by the difference between the average and either number, and then multiply it by 4, you get the square of the even number. The average and the difference are both perfect squares. It's not a coincidence. Why do all Pythagorean triples seem to follow this pattern? What's really going on behind these triples? Pythagorean triples are sets of three natural numbers, satisfying Pythagorean theorem. In fact, they can be classified into two categories: triples where all three numbers are coprime, and triples that are multiples of those. Here, any two of the three numbers are relatively prime. The coprime ones are more fundamental, so we call these primitive Pythagorean triples. Let's focus on these primitive triples. In all primitive triples, one number is even and the other two are odd. The largest number is always odd. Why is that? Assume A, B, and C form a primitive Pythagorean triple. First, can all three numbers be odd? No. In this case, three numbers are expressed like this. The square of any odd number is also odd. So the sum of two odd squares is even. Since A, B, and C satisfy the Pythagorean theorem, the left side must be even, but the square of an odd number on the right side stays odd. That breaks the equation, so all three can't be odd. What if two of them are even? Then those two numbers share a common factor of 2. That means the triple isn't primitive, so that's not allowed either. There's only one possible structure left: two odd numbers and one even number. But which one is even? Let's test the case where C is even. Since C is an even number, suppose C equals 2m. So C squared equals 4m squared, which is divisible by 4. Then a squared plus b squared on the left side must be also divisible by 4. Since a and b are both odd, a squared b squared equals this. The remainder is 2. It can't be divisible by 4. Again, a contradiction. Therefore, C must be odd, and either A or B must be even, just one. This forces the triple into a very specific structure. Now, let's prove the most interesting pattern algebraically. Let A be the even number and B and C be odd. C is the largest. The average of any two odd natural numbers is always a natural number. Let's define the average of B and C as S. Then we can write B equals S minus T, C equals S plus T. T is the difference between S and B or S and C. Substitute these expressions into the Pythagorean theorem. Now simplify. So the square of the even number A equals 4 times the product of S and T. This confirms our earlier observation. Pythagorean triples are not just numerical coincidences. They hide deep structure, symmetry, and algebraic beauty. Have you ever heard about this pattern? Feel free to share your thoughts in the comments. If you enjoyed this math traveling, don't forget to like and subscribe for the next trip.